We're now going to start looking at how to analyse circuits and calculate the voltages, currents and resistances in a circuit. And we're going to do that using Kirchhoff's laws as well as using Ohm's law. So there are two laws that we need to be aware of that are known as Kirchhoff's laws. The first one we're going to call the junction or it's sometimes called the current law. So in both cases that will hopefully help to identify what the law relates to and where in a circuit it's relevant. And that's simply that the sum of the currents entering a point, so hence the idea of a junction. So sum of the currents entering a point will be equal to the sum of the currents leaving that point, which kind of makes sense when you think about it, in that whatever you've got going in has to come out. We can't have current disappearing. And so it's just a simple matter of sum of the currents entering being equal to the sum of the currents leaving that point. And the way that that's represented in the data booklet, I don't think it's all that useful. It's represented this way. So that's the representation in the data booklet, as I said, so I'll just highlight that. But I think a more useful way to understand it is to separate that out into the currents that go into a point and the currents that come out of a point. So I think that's a slightly more useful way to think of it. In that if we had, say, one current going in and two coming out, then I1 is equal to I2 plus I3. But if you then sort of take them across to the one side, then I1 minus I2 minus I3 will equal 0. So that first equation there is relevant, but it's probably not the easiest way to make sense of Kirchhoff's junction law. The second one is known as the loop law, and again otherwise known as the voltage law. And it's very similar, but a different part of the circuit that we're going to look at. So instead of being a junction, we're going to look at a loop. And so it's looking at the sum of the EMFs in a loop being equal to the sum of the potential differences. Now remember here that both EMFs and potential differences both a form of voltage, and hence why it's called the voltage law. But just to separate them out and make it a bit clearer, we're going to refer to them here as EMFs and potential differences. And again, a not particularly helpful way of representing it in the data booklet. So the sum of the voltages in a loop are going to be equal to 0, and that's indicated as being the loop law. So again, that's the one that's in the data booklet, but again I think it's more useful to identify that it's the sum of the voltage inputs being equal to the sum of the voltage outputs. Now to make a little bit more sense of this, let's have a look at it in a diagram, and we'll just sort of generalize this scenario. So we'll start off with a battery at the top with an EMF of Vs, and we'll keep it a fairly simple circuit. We'll just have a loop through here with a single resistor, and another loop with two resistors. And we'll label them RA, RB and RC, and we'll also need to look at the currents that are flowing in the circuit, and so we'll identify that this current here is going to be current I1, and then we're going to have current I2 flowing down through here and current I3 going across this way. And if you sort of track that current I1 back, you can see that it's actually going to be the same as the current flowing through that branch as well. So if we first of all look at the junction law, to make it clearer here too, let's label this point X and this one point Y. At that junction X, we've got one current that's going in, so I1 is going into that junction, and we've got two currents coming out being I2 and I3. So that would be the application of the junction law there. If we then look at the point Y, we have the opposite. The currents that are going in are I2 and I3, and the current coming out is I1. You notice that those two lines are basically the same, just flipped around. Not a useful calculation there, but just something to be aware of. Now, it might be the case that you don't really know what I3 is. You might need to calculate that using Ohm's law if you know what the potential difference across RA is and you know the resistance RA. So in some cases you'll need to use Ohm's law first in order to figure out these currents, or you could even just substitute that straight in there, and instead of I3 you could write that as whatever the potential difference is across R3 divided by the resistance in R3, and you could substitute that into the equation there as well. Now, the second law that we're going to have a look at here is the loop law, and I'm going to identify these loops. So the first loop that we're going to look at is around here. So we're going to call that one loop 1, and in loop 1 we have the input is going to be Vs, so the EMF that's being supplied in that loop is Vs, and there's only one output, and that's going to be the potential difference across this resistor RA. So we'll call that VA. So that means that Vs is going to be equal to VA. So pretty straightforward situation there. The second loop we're going to look at is around the outside. So it's going to encompass those two resistors down the bottom. Notice that it doesn't worry about that loop across the middle. That's fine. We're only interested in that loop starting from the battery, going around the circuit and ending up back at the battery. We don't have to pass through all of the components in the circuit. So in loop 2, we're going to now have to consider this potential difference here and this one here. So that one will be VB and this one will be VC. And so in loop 2, we have that Vs is going to be equal to VB plus Vc. Now you can see there that Vs is equal to Va and Vs is equal to Vb plus Vc, so we can identify that Va is equal to Vb plus Vc. We can also do that using a third loop. Now this loop is not always a loop that's considered in these sort of scenarios, but we do actually have a loop here as well. We'll call this one loop 3. Now for loop 3, we don't actually have any EMFs. So the supply voltages, or the input voltages, are going to be 0. We don't have EMFs in that loop, and so we can't indicate any inputs. We have 3 outputs, but we need to be careful about these. If you look at the direction of the arrow that I've drawn here, going in an anti-clockwise direction, we're going in the opposite direction to the current I3 as we move around that loop in that anti-clockwise direction. So we're not actually dealing with VA, we're dealing with negative VA because it's in the opposite direction to the current flow. That means that we're going to have negative VA plus VB and VC. Now we can rearrange that to show that VA is equal to VB plus VC as we identified by looking at those first two loops. Now they're the applications in a very sort of nondescript circuit. We'll have a look in a bit more detail in class at applying those laws to some circuits and calculating some unknown quantities of current, resistance and potential difference.